In this presentation, we continue to talk about power for an alternating circuit or a alternating current, alternating voltage circuit that has resistors, capacitors, and inductors. And we define something called the apparent power for a circuit. So previously we had real power, and real power came from the resistive part of the circuit. Real power is something that occurs when the load has resistance in it, and that resistance can use that power in the circuit. It doesn't give it back to the source, so you can dissipate heat, for example, with a resistor. And so the power for the real power can be written as the current times the voltage. Of course, this is the current through a resistor, voltage across a resistor, and these are always the effective values. And then we could use Ohm's law to write it, of course, in terms of the resistance or the voltage. We also define something called the reactive power, and reactive power comes from capacitors and inductors. If it's a capacitor, the reactive power is negative. If it's an inductor, the inductive reactive power is positive. And we said that the reason that we define this reactive power is because if we look at a capacitor or an inductor in a circuit and we look at the average power for those components, the average power is always zero, but the instantaneous power is not necessarily zero, and so we have to take it into account. So again, we define reactive power as this Q value, and it's also written as the voltage times the current, or the current times the voltage, where these are the effective values, and if it's an inductor, these would be the values across the inductor and through the inductor. And then, of course, using the equivalent of Ohm's law for AC, we could write it in terms of the inductive reactance, or in the case of a capacitor, the capacitive reactance. So we've got real power, which actually can be used in a circuit to do work. So in the case of a resistor, it can dissipate heat. And then we have reactive power, which does not do any real work in the circuit, but it actually can store energy and then release energy back into the circuit. So because all of these terms, both for real power and reactive power, seem to be defined in the same way in terms of being the current times the voltage. So if we were talking about real power, it would be the current through the resistor, the voltage across the resistor. And if we were talking about reactive power, it would be the current through that reactive component, capacitor, inductor, times the voltage across that capacitive or reactive components. And so it seems like, in general, both of these have the same form in terms of depending on current and voltage. And so we're going to define something that's called the apparent power. The apparent power is written as an S, and it's defined as the total current, the total effective current that's coming out of the source times the total effective voltage from the source. So where previously the current and the voltages were represented in terms of the current across a particular component, this current is actually the total current that comes out of the source, and this V is the total voltage, the maximum, not the maximums, the effective values. In order to distinguish apparent power from real power and also from reactive power, we write it in units of VA. So, of course, where does this come from? Well, we have our voltage is measured in volts and our current is measured in amps, and so we just write it as VA. This is different than VAR. VAR is the unit that we use for reactive power. So now we have three powers. We have real power, reactive power, and now we have this thing called apparent power. So because of the fact that the current here and the voltage are represented by the amount coming out of the sources, we can use the equivalent of Ohm's law for AC, and we can write the voltage is the current times the impedance, where these are all the effective values and the amplitude of the impedance. So this is not phasor notation here, right? It's just simply, I mean, you can write it in phasor notation, but these are just the amplitudes of these terms. So we could write the apparent power as current times voltage, or using the equivalent of Ohm's law for AC, we could write it as the current squared times the impedance. or voltage squared divided by the impedance. So again, this looks very similar to those other two expressions that we have for power, the main difference being that now we've replaced resistance or reactance with the total impedance in the circuit. So why are we doing this? Well, there's a reason that we're doing this. The value for the apparent power, which has units of volts times amps or kilovolts, kilovolt amps, along with a voltage rating, can actually tell us the current rating in the circuit. So for example, suppose we had an apparent power rating of 250 kilo VA, and we had a voltage rating of 4.16 kilovolts. Using the apparent power rating and the voltage rating, we can figure out what the current rating in that circuit is. So the voltage is 250. Excuse me. The voltage is 4.16 kilovolts. The apparent power is 250 kilo VA. So we have 60 amps for our particular circuit. So we're going to talk about that a little bit more here in a minute and see, why is that important? Before we do that, let's just see if we can sort of identify the relationships between the real power, the reactive power, and the apparent power. So we go back to our impedance diagram, and we know that we can write down the impedance as having some, in terms of polar form, it has some value associated with it, and then it has some angle associated with it. And we know that if we have the impedance, we can always find the resistance in the circuit by taking the impedance value and multiplying by cosine of the angle, and we can find the reactive component by taking the impedance value times sine of the angle. This particular representation for the impedance would be inductive because my angle is a positive angle, and of course this triangle would just be flipped into the fourth quadrant if it was capacitive, so it doesn't matter, it's the same analogy. So if I took my representation for impedance and I multiplied the impedance value by the current squared, where the current here is the effective value. Again, we're not using phasors, we're just using sort of the magnitudes of these phasors, then I would get the apparent power. So along the hypotenuse, multiplying this side by the current squared, I would get the apparent power. Well, it turns out that if I multiplied each side of the triangle by the current squared, I would end up getting the power, the real power, along the horizontal axis, and I would get the reactive power along the vertical axis, right? So basically, starting with my impedance diagram and multiplying all of the sides by the current squared, again, just the effective value of the current squared, then I get these representation, this triangle representation for the apparent power along the hypotenuse, the real power along the horizontal, and the reactive power along the vertical. And so, we know that we can write power as the real power as the current squared times the resistance. And of course, that's the same thing. Resistance is just the total impedance times cosine of the angle, so I could substitute that in. And I could do the same thing for the reactive power. It's the current squared times the reactance. And the reactance is just the impedance times sine of the angle. So one of the things that we should notice from this triangle here is if I redraw my picture, I have my apparent power along the hypotenuse, I have the real power along the horizontal, and then I have that reactive power along the vertical, and I should be able to use trig identities to find a relationship between those. So I realized that if I wanted to know the apparent power, I can find that by taking the square root of the real power squared plus the reactive power squared. And the other way around, if I know the apparent power, I can figure out what the real power is by taking the apparent power and multiplying by cosine of the angle. And then I can do the same thing for the reactive power. I can take the apparent power and multiply by sine of the angle. So I have this relationship where if I know what the impedance in the circuit is, I should be able to calculate what the total apparent power is, and I should be able to calculate the real and the reactive powers because they have this relationship between them. So this is just a summary that we can now draw this sort of where we had this impedance diagram. We can now draw like a power diagram where we have our real power, our reactive power, and our apparent power. And we know that there is this relationship between them, so we can always calculate the apparent power from the real and the reactive powers. And the other way around, if I know the apparent power and I know the angle here for my impedance, then I can figure out what the real and the reactive powers are. So the V and the I here are always the effective or the RMS values in our circuit. We're not using phasor notation. It's just the actual effective values without the angles. Theta is always the phase angle between the voltage and the current, or more specifically, it is the angle of our impedance value. Our Q value is going to be positive if it's an inductive circuit, and it's going to be negative if it's a capacitive circuit. Or if another way to say this is if the inductance dominates, it would be positive, and if the capacitance dominates, it would be negative. We also have something that we define called the power factor, and the power factor actually provides a value that tells us the fraction of the apparent power that goes into real power. So this power factor is the actual power in the circuit, real power, over the apparent power. The apparent power is just current times voltage. The real power is the current times the voltage times cosine of the angle. So the power factor is just cosine of the angle. So obviously cosine of the angle can be anywhere between, well, in terms of our angles, our angle can go from minus 90 to plus 90. So our cosine values basically can be anywhere between 0 and 1. So if this ended up being 0, then that means that I don't have any resistance in the circuit. So the power from the resistor is just 0, and everything in the circuit is reactive. And if cosine was equal to 1, then that means I wouldn't have any reactive components in the circuit. Everything would be resistive, and all of the apparent power would come from the real power. But it can be anywhere between 0 and 1, and it's telling you a fraction. So if it was 0.5, for example, for your power factor, that would mean that 50% of the apparent power was going into the real power. And of course, the other 50% would be going into the apparent, or would be going into, excuse me, the reactive power. There's a lot of power terms. Let's consider an example. So why do we want to rate equipment in terms of apparent power rather than real power? So here's an example. So suppose that I had some device that was rated for a real power of 120 kilowatts and a maximum voltage of 600 volts. So I only have a resistor in this particular circuit, and suppose that I have this resistor set up in this particular case so that it is drawing the maximum amount of power possible, so 120 kilowatts. So my power is 120 kilowatts. I don't have any reactive components like a capacitor or an inductor in this circuit, so the reactive power is 0. So that means my total apparent power for this circuit is all real power, and it's just 120 kVA. So what does that mean about the current that's possible in this circuit? So we know that the current is just the apparent power over the voltage. The apparent power is 120 kVA, or 120,000 VA. The voltage is 600. So as we think about this, I didn't mention this in the very beginning, but this is an AC source again, right? So this 600 is essentially the effective value for that voltage supply, but it is still oscillating in time. So if I divide this out, I get 200 amps. So this means that if I have this resistor connected so that I have the maximum power that is possible, the maximum amount of current that I should draw in this circuit is 200 amps. And if I draw any more than that, then I'm going to have a problem with the circuit. This is similar to resistors that have a power rating and a voltage rating on them. So resistors are built to only be able to dissipate a certain amount of heat, and so if you put too much current through those resistors, they actually will get extremely hot, and they can, they can burn up, or they can, there can be issues there. So this is the same thing here with a particular maybe generator here that really is only meant to generate a certain amount of current in the circuit. Suppose we took that same exact circuit, but we put an inductor in parallel with the resistor. So the resistor is still drawing from the source, and it still has a power rating of 120 kilowatts. So that particular resistor is still, dissipating energy according to this power rating. But my inductor also has inductive reactance, right? So it is connected to that 600 volts that's AC, and so it has reactive power, in this particular example, of 160 kiloVAR. So what does that mean about the apparent power in the circuit? So the apparent power is just the real power squared plus the reactive power squared. So if I take those two terms, square them each, take the square root, I get 200 kiloVA. So if I take the apparent power and I now calculate what the current is that could be drawn in this circuit, the maximum current, it would be the apparent power, 200,000 VA, divided by the voltage of 600 volts, and I get 333 amps. So there's my 333 amps. And I have this poof here because this circuit is overloaded. It was only meant to have a rating of current in that circuit of 200 amps, and at some instant in time, the current that's actually coming out of there is 333. So by rating the equipment in terms of real power and voltage, we have a problem when we put reactive components in the circuit. So is it possible to have these reactive components in the circuit and maybe cancel them out? And so the answer to that is yes. We can actually cancel that out by adding another reactive component that's the opposite type. So here's my voltage supply again, same voltage supply. Here is the two components that are together now, and they are producing a power rating of 120 kilowatts and a reactive power of 160 kiloVAR, which is inductive. And if I put a capacitor in parallel with those components, and I make sure that capacitor has the same amount of reactive power as the inductor, then I could figure out what the total power is in that circuit. It's still 120 kilowatts. But the total reactive power is the combination of the inductive reactive power and the capacitive reactive power. And when I add those two components together, because they have the opposite sign and the opposite impact on the circuit, it ends up giving me 0 reactive power. And now we're back to the same apparent power that we had before when I didn't have any reactive components in there, which is 120 kiloVA. And if I calculate the current in that circuit now, I'm back to what that maximum rating is, which is 200 amps. So even if you put those reactive components in, you can also counteract them by putting the opposite type of reactive component in the circuit. But hopefully this explains to some extent why apparent power is actually really important. So the apparent power is actually going to give us a better idea of how much current is actually being drawn from the voltage supply, that sort of that maximum value, or that maximum or the effective value of that oscillating current.